Riemann's approach to integration just follows roughly the intuitive idea why the Newton definite integral must work. Why would we like to go for some other approach if we know it must work? So the problem is that without some more straightforward definition, we have a problem. We face the problem: what are the integrable functions? How will we define or decide whether there is a primitive function? That's a really difficult problem from scratch, right? And so just by the properties of the derivatives, we know that the functions admitting the antiderivative will form a vector space. That's nice, but otherwise we don't know much about. So it's good to come up with a smarter idea, more special, more explicit, and that's what Bernhard Riemann did in the middle of the 19th century. So roughly speaking, you can compare the pictures on the left and right. So on the left, we simply work with some expectation how the things should work, if they are nice, if the functions are nice enough, and we approximated the interval values of f by the value in the left beginning of the subinterval. Instead of that, we simply take a partition of the integral x0 in interval ab into the point x0 to xn like we did before, and for each of the subinterval we pick up some xi1 through xin, which will be the representatives. So inside of the why doesn't it make here? Inside of the individual interval, we simply pick up some representatives xi, and then we approximate the area below the graph by the area of the rectangle. And now we say, now we just choose these representatives, this partition with representatives, and we say that the norm of the partition is some nu if the maximum of all the lengths of the subintervals is less or equal to nu. Or we can say that nu is just the maximum. And now we say that the Riemann integral of the function on the interval ab exists if for every sequence of partitions with the representatives where the norm converges to 0. So it's very many of choices there, right? So unimaginably many. But we insist that whenever we do such choice of a sequence with norms del k approaching 0, then there must exist the limit and be all the time the same value of s. And then we simply write that s is the integral from a to b of fx dx. In view of the intuitive justification of the definition of the Newton's finite integral, so we should expect that the two things will finally be equal for nice f. But let us see. So that's a bit of our challenge in this video. So of course, just by the very definition and by the rules and properties valid for limits, which we know, so we see that the Riemann integral will be well working again on a vector space on integrable functions, and it will be itself a linear functional. It means that the sum, well, it will be, no, I was too fast. So it's a linear functional is the condition 2 and 3, but at the same time it's additive with respect to the intervals we integrate over, right? So we can split the interval AB into disjunct union of 2 or more, but then only finite one in the end, and that's also true. So it's finitely additive, linear functional so finitely additive with respect to the intervals and linear functional with respect to the vector space structure on the space of integrable functions. So that's straightforward and nice. And now we come to the absolutely crucial thing for all the mathematical analysis, I mean the infinitesimal one. I mean the infinitesimal one, because it's just saying that whenever the function f we deal with is at least continuous, just enough to have a continuous function on AB, then the function is integrable, and the entire Riemann integral is providing us with the antiderivative if we consider it as a function of the upper bound. So that's a very crucial result, and the proof is quite straightforward. It just is based on several observations. So first of all, having the function f continues on the closed interval AB, finite interval AB, then clearly f must be bounded. And for bounded functions, we can simply replace the choice of the representatives of our partition of the interval by taking the suprema and the infima. So if the function f was not only bounded but also continuous, we could write maximum and minimum here. But we are happy in this spot, in this step with bounded functions. And so we can always take over the representatives, instead of representatives, to take the supremum and infimum. And because if you can imagine, if you just refine your decomposition of the interval AB to subintervals, then the supremum estimate, so the finite Riemann sum, will become smaller or equal, and the lower with the infima will become bigger or equal. And clearly the sup one is bigger than the small one. So if we do the refinements so that the norms will get to 0, we clearly get two sequences which are, so one is non-increasing and bounded from below, and therefore it has got limit, and one is non-increasing and non-decreasing, bounding from above, therefore it has got a limit, and non-decreasing and bounding from below, therefore it has got a limit. And these two limits are called the upper and lower integrals, or also Darboux integrals. And it's quite easy to show that the Riemann integral exists if and only if the upper and lower integrals are equal. So this is not difficult, and intuitively I think it should be completely clear. Now to conclude the final result, that means that for continuous functions the upper and lower integrals must be equal. This follows the concept of uniform continuity, and we talked about it already. So a function f is uniformly continuous if we can do what we request for continuity normally only for individual points and their small neighborhoods, and now we request it for whole intervals. Now so on the whole interval we request that if we request the difference of values to be less than epsilon, then we must be able to find delta, so that the difference of arguments less than delta will ensure that. And this is something which is depicted on the picture, and it's quite clear that for continuous functions on a bounded closed interval it must be true, because there we have got the delta, and for fixed epsilon we have the deltas for each point, and that will be a covering of the interval by open subspaces. And we know that there is a finite covering out of that, and so the minimum of the deltas from this finite covering will be just serving us with the results. So this is a very important theorem which works always, and this allows us to finish the proof, because we simply get the uniform continuity as a tool to see that actually the lower and upper integral must be the same. Few final remarks due. Well, so first of all, of course, notice that if we have got if you have got something like a piecewise continuous function, so here will be a, here will be b, and then you have functions like this, right? So there will be jumps here, these points. Then we of course can always split the interval into 3 intervals, this one, and this one, and use the theorem as we saw it. So for all piecewise continuous functions, which would mean that we need to have the one-side limits, right? Because if we have got the one-side limits, then we can consider the function as being continuous on the closed subintervals, and then the result implies that we can do it. I mean, of course, thinking about the theorem itself, what does it mean that we know that for each continuous function we have got the antiderivative? That's an amazing thing, isn't it? Because you would think that if a function is differentiable, so it has got derivatives everywhere, then perhaps it should be a nice function, whereas the continuous functions might be really ugly. They might be wiggling a lot. And still, for any continuous function, whatever horrible it would be, you find the antiderivative. So it shows that in some sense our menagerie, our zoo of functions is in some sense too big. Yeah? So you have too many naughty animals there. So that's a very, very nice thing. Right, I think that's enough for this week.